Good morning, class, on this beautiful sunny day. Today we're doing the last lesson in our kinetics and equilibrium topic called Common Ions in Equilibrium and Entropy. And the reason why I held off on the common ions is I wanted to make sure you understood equilibrium first. And then we're going to see that the common ions is a solutions connection to equilibrium. And then entropy is the final piece of the puzzle to understand mechanisms and reaction energy. So let's get into it. Common ions in equilibrium connects the concept of the solution process to equilibrium. So what does this mean? If you know how a solution reaction works through ionization or dissociation, and you know how to tell which way a reaction will shift under a stress, it's pretty easy to do. And this is because once you know what ions are present, you can determine which side of the reaction the ions are going to affect. And then if I'm adding, as we always said in equilibrium, adding, the reaction shifts opposite. So when a solute interacts with a solvent and the two things are soluble, the ionic salt ionizes or dissociates into its ions in solution. So the first thing we have to do here is remember how this reaction works. So if I take a sample of calcium sulfate solid and I place it in water, because calcium sulfate is ionic and water is polar, it's going to dissolve. It is soluble. And what I'm going to get is calcium ions and sulfate ions in solution. Again, this is very important because if I add this to a reaction at equilibrium, okay, it's these ions that are going to affect the equilibrium. Solids do not. Another example, we have here some sodium fluoride, which is ionic. Place it in water. It's going to ionize into our Na plus and F minus ions. All right, so we have to understand how this works to apply it to our equilibrium charts. So let's take a look. When we understand ions and equilibrium, I can understand the total reaction process. So it says here, which way will the reaction below shift when NaCl aqueous is added? So the Na and Cl is already dissolved in water. Let's take a look at the reaction. I have magnesium chloride with energy. Remember that from kinetics is endothermic. Energy is on the left, it's absorbed. And that has to happen because when you're dissolving, you are pulling apart this ionic salt into its ions, ionization. And notice I get Mg plus 2 and I get chlorine minus, and there's two of them because of the 2. Okay? Well, if you look at this reaction, there is no NaCl. So I have to understand that NaCl aqueous actually consists of Na plus ions and Cl minus ions. So I have to be able to write this reaction out in order to analyze what's going to happen in the equilibrium. So if I know that the Na and the Cl ions are present, that tells me I'm really adding in the solution Na plus and Cl minus. Now, if you look up here in this reaction, there is no Na plus, but there is Cl minus. So we're actually adding Cl minus ions. So at this point, we can then assess the equilibrium of how it's going to shift. So if I'm adding NaCl aqueous, I'm actually adding Cl minus ions. So I'm going to add here on the product side. And as you learned, when you add, the reaction shifts opposite. So the question says, which way will this reaction shift? It's going to shift to the left in the opposite direction. So if I had a chart, as we know how equilibrium works with a seesaw, I add on the right. So the right side is going to go down and the left side is going to go up. So I'm going to cause precipitation to occur to make magnesium chloride solid, and I'm going to increase the amount of energy. Again, not hard to do as long as you know which reactions occur. Let's do one more example. Which way will this reaction shift when sodium sulfate aqueous is added? Now take a look at the reaction. I have sodium phosphate, an ionic solid, that's dissolving in water to give me my ions. Na plus ions and phosphate ions. The reason why it's 3 is because it's Na3. Now, I am adding Na2SO4. Notice that's not here. So I have to understand how this works first. So Na2SO4 actually consists of Na ions and sulfate ions. So if I'm adding Na2SO4 aqueous, this is what I'm adding. And notice that sulfate is not here. So when sulfate is taken out, what am I actually adding? I'm adding only Na plus. Notice how I put the arrow. And where is it? It's on the product side. So this also will shift to the left. So you're going to get in equilibrium questions sometimes things that are not in the reaction directly, but you have to understand when they dissolve, they make ions that are inside the reaction. So again, that's the common ion and equilibrium connection. The last part of our discussion is on entropy. And entropy, I like to say, is enthalpy's cousin in terms of thermochemistry dynamics. Entropy, notice this substance has low entropy, but this one has high entropy. Gives you an idea of what you're actually going to see. Entropy gives us the last piece of our thermodynamic puzzle. We've already learned that studying reaction rates and mechanisms involves heat, and heat's an important part of the process. But to completely understand how the reaction works, we must also become familiar with its entropy. Again, thinking about that first slide with entropy tells us that low, you're together, high, you're separate. Well, what does that actually mean? When we're actually looking at entropy, entropy gets a symbol of delta S, and it's defined as a measure of the degree of randomness of the particles or molecules in a system. So if you go back to that picture, that first picture was of all these little spheres stuck together in a nice order. Randomness was not being shown. That's why it was low. But on the picture to the right of that, we saw the particles all scattered. Well, that's random. That's what entropy is all about. When we analyze entropy, entropy and energy go together. And that's because as kinetic energy increases, entropy increases with it. Now, what's the connection to earlier topics? Remember, kinetic energy, average kinetic energy is temperature. So if I increase the temperature, my entropy increases. To give you a visual of that, we can go way back to our particle diagrams. Notice that solids are very close together, liquids a little further apart, and gas is the furthest apart. Well, energy-wise, we said, if the particles are not moving freely, they're going to have low energy. But if they are able to move all over the place, well, you're going to have high energy. Well, how do I get a solid to change to a liquid, to change to a gas? Exactly. I have to add heat. So if I'm adding heat and increasing kinetic energy, I'm going through these phase changes. And what I see is solids then have to be not random, very organized, and gas particles are going to be totally random and no organization. So the kinetic energy that's being transferred pushes the molecules away, increasing entropy. Now, if that's the case, well, just like with kinetics and how to make things go faster, I can also do things to affect the entropy. If you can recall, the symbol for entropy was delta S. I like to associate the S for spacing of particles, because if there's no spacing and they're tightly compacted together, it's low. But if there's a lot of space, S, then it's high. Which means if I wanted to increase entropy, it's easy to do. As we saw on the last slide, if I increase temperature, particles get further apart, solid to liquid to gas. So my particle space increases, entropy increases. But I could also apply other reaction concepts. I can decrease the pressure. If I take my box, right, and I decrease the pressure, I'm increasing volume, right? Well, if they get further apart, I'm increasing spacing. Entropy goes up. That's why pressure and volume go together. And lastly, if I increase the surface area, I'm also increasing particle spacing. Okay, remember that in order for a reaction to occur, you have to have an effective collision. And we learned that if we increase the surface area, we get more effective collisions. What's the reason? Also here is entropy. The more particles I have that are able to move around, the more space they create in between them, increasing the actual entropy. So if I understand how this works, I can make a nature and energy and entropy connection. And this connection of entropy and energy is essential because both affect how nature and spontaneity work, how reactions occur on their own. And what we find, and it's a very important concept in chemistry, is that nature always favors spontaneity. Spontaneity arises when you have a high entropy, positive delta S, and a low energy. The only way to get low energy is if the reaction's exothermic, and that's why it's negative delta H. Very quick connection that we can make to nature. If you left your yard untouched for a few months, things would grow out of control. Weeds, trees, bushes, everything goes crazy. Well, that's because nature likes and favors chaos. If left alone, it grows randomly, and that's why randomness increases. In nature, when energy in the atmosphere builds up and builds up and builds up and builds up, the atmosphere gets very unstable. What happens? A storm, hurricane, tornado, thunder, lightning. All of those systems release energy and bring nature back to a very quiet state. The connection I always like to make is always after a huge rainstorm or a snowstorm, there's always a calm in the air. The sun always comes back out. That's nature favoring certain conditions. And if we were taking the Regents exam, we would have to know how this concept relates based on these factual pieces. All right. So as always, you're going to do the worksheet, submit it, and that is it for kinetics and equilibrium. Next week on Tuesday, I will post some review questions. And then next Thursday will be your assessment on kinetics and equilibrium. Have a great day.